More section 6.2. We're working on exponential growth and decay. So this should really be a review of what we saw in our pre-calculus class and even our algebra 2 class with trigonometry. So exponential growth and decay function. We've seen this thing before. So a little bit of a review. So remember that C is your initial amount. So your initial amount. Y is your final. K is your rate of growth or decay, and if we know that if it's positive, it's a growth, and if it's negative, it's a decay. And then last but not least, T is time, and the unit of time will be dictated by the context of the problem. Half-life. Half-life is something that seems to give people a lot of difficulties. Remember, with half-life, it's the amount of time it takes for 1/2 of the original amount to decay. So what I'm looking for in that situation is I'm looking for my final amount to be exactly half of what my original amount was. So that's what we're going to know, and we're going to solve for the time at which that happens. So remember, half-life, we're talking about half-life, we're talking about a time. Okay, half-life, we're going to be talking about a time. Doubling time, how long is it going to take my original amount to turn into twice what it started as? So there's your background. Hopefully that's a nice review for you. So let's go down and let's take a look at this. Probably going to want some calculator kind of stuff involved here. Radius has a half-life of 1,620 years if 1.5 grams is present after 1,000 years, and radium follows the law of exponential growth and decay. Oh, okay, so I see that. Exponential growth and decay. As soon as I see that, y is equal to CE to the KT. How much is left after 10,000 years? 1.5 grams is present after 1,000 years. So let's kind of list that as what we know. So we know that at time 1,000 years, we have 1.5 grams. How much is left after 10,000 years? At time 10,000 years, we want to know how many grams we actually have. So we don't know what our initial amount is, but if we want to use time 1,000 and time 10,000, might make things a little bit more concrete. So let's say we use time 1,000 and the amount is 1.5. So I don't know how much I'm beginning with, but I know I have 1.5 grams at 1,000 years. So K times 1,000. Well, that's all well and good. The issue is, in that red equation that I just wrote down, I don't know K and I don't know C. So now it's become a classic 2-equation, 2-variable problem. I need to come up with a second equation in order to help me figure out what I'm looking for in order to come up with either C or K. And where that's going to come from is this half-life statement. Radius has a half-life of 1,620 years, which means at time 1,620 years, we have 1/2 of our original amount. Half of what I started with, right? I'm starting with C. I now have half of it, E to the K times 1,620 years. So we were given the red point over there. At 1,000 years, we have 1.5 grams. We were also given at 1,620 years, we have half of what we started with. So that's almost a good thing to think about. At 1,620 years, we have half of what we began with. So now, I don't know if that helps or not, but now working backwards to find out what K is. Well, these C's are going to cancel each other out. They're going to be gone. So 1/2 is equal to E to the 1,620K. Take the natural log of both sides to get the variable out of the exponent. Natural log of 1/2 would be the same thing as 1,620K. So K would be the natural log of 1/2 divided by 1,620. Now, you could certainly go to your calculator and figure out what that is. And in fact, we will too. But I'm going to have a suggestion for people. Do not make a decimal out of that number. That I just wrote down is an exact value. So if you go to your calculator, and I've got my Inspire ready to go here, and I say, all right, I want the natural log. Whoops, sorry, I'll go to my scratch pad. And if I go to my scratch pad, and I go, all right, I want the natural log of 1/2. Use my arrow to get out of there so I can jump past this thing. Divided by 1,620. I'll know what K is. So there's what K is. It's a negative number. We're going to be decaying at a pretty slow rate. But there it is. Do not round that to 3 or even 4 decimal places. Instead, store that number. So if you're on an 84, get that number on your screen just like I have, and use the store command, STO with the arrow. On my Inspire here, it is the control function of the variable button. I want to store that number. Well, what did I call it? I called it K, so let's store it as K. And when I hit enter, from now on, whenever I type in the letter K, I'm going to get that number back because I have it stored. So now that I have that stored, let's go back in and see what I have. And what I like to do to remind myself, when I store this number, right, so I've now got this number stored, right, I've stored it, I put a little circle around the letter itself so I'll remind myself that K that I need is going to be very helpful. So now when I look at solving for my C, let's come back over to this red equation over here. We now know that this K that I found plays a role. I figured out what K is, and I'm going to use that K button to my advantage because now my C that I'm solving for is going to be 1.5 divided by e to the 1,000 times that new stored K value. And that'll tell me what my C is. So let's say that I go and do that. So let's go back to my calculator again. So now I have 1.5 divided by e to the, I'm going to multiply two numbers together, 1,000 times my K value that I had stored. And notice on my Inspire, my K now is bold-faced, which means it's the one that I have stored. When I hit enter, there's my new C value. Now, again, for those of you guys that are worried, oh, I'm going to round wrong, and you should be worried about that because a little bit of a rounding error when we're talking about this type of precision can cause big trouble later. So let's store it again. But what should I store it as? Well, this is C. So let's store this thing as the C value I'm looking for. There you go. I have this very lengthy decimal stored as C. Calculator's only trying to show me six sig figs with it. But now when I go back, I've got my C stored. So I'll do the same thing again. Now let's store this thing as my C value. So I have two things stored in my calculator. Now let's answer the question. So at time 10,000 years, my Y is equal to that 10,000, or I'm sorry, my C value that I figured out that I have stored, e to that K value that I have stored times 10,000 years. And if I now take that thing and go to my calculator and have it punch it in for me, I'm going to punch in C e to the 10,000 times my K power. Notice the C and the K are both bold-faced, and that E is already known to be a special value in the calculator. Punch that in, and it looks like I'm going to have 0.03, and if we're going to three decimal places, 0.032 grams would be my final value. So my final value, 0.032 grams if we're rounding it to three decimal places. And the nice part about it is you know you didn't screw up the rounding because the calculator took care of all your exact values for you. All right, second one. Initial investment of $10,000 takes 5 years to double. If interest is compounded continuously, what's my initial interest rate? So it's interest compounded continuously. A equals PE to the R times T. Or for those of you playing along at home, that's the exact same equation as the one we used above. Y equals CE to the KT. A is your final amount, P is your initial amount, R is your rate, T is your time. So what's my initial interest rate? Well, it's going to take 5 years to double. So my initial value, at time 0, I have $10,000. Well, we want to know how many years it's going to take to double. So we're finding doubling time right here is really what it comes down to. So I'm going to set this up. So my final amount I want to be 20,000. And that's my initial amount is 10,000. E to the K, or I'm sorry, E to the RT. Well, what's R? We don't know what R is. That's what we're solving for. But we know it takes 5 years for this to happen. So now we're going to solve. So now if I'm going to solve this equation for R, let's divide both sides by 10,000, or by 10,000. Magically, 2 is equal to E to the 5R power. Anytime you do a doubling time problem or a half-life problem, you're going to get an equation like this one right here. Half-life, you're going to end up being E to a power is equal to 1/2. Doubling time power, the problem. you're going to end up with an equation that looks like 2 is equal to e to some power. So now when I go to solve this, let's take the natural log of both sides. So my r is the natural log of 2 divided by 5. Again, I would store this. So my interest rate, let's store that number. Well, let's go figure out what it is so I can answer the question, because my question says what's the rate. So let's go punch in natural log of 2. And make sure you jump out of the natural log before you divide by 5. Hit enter. So it looks like 0.13862. Now you could store that thing as your rate if you wanted to. Store that thing as your r if you wanted, or you could certainly store it as decay. It won't matter for it. We're only using that for the problem that we're dealing with. So I have this thing stored. So it looks like as a percentage that would be 13. Move the decimal place 2 places. 13.863% for the rate here. But I know I have it stored as r. It looks like 13.863 to go accurately to 3 decimal places. How much will be present after 12 years? Well, now we're going to use that r that we stored. So my initial amount is 10,000. My final amount is what I'm looking for. E, I've got my r stored times 12 power. So let's go let our calculator do the heavy lifting for us. So 10,000 e to the r times 5, or I'm sorry, times 12 years, sorry, power, punch it in, looks like 5,270. Oh, wait a minute. I wonder if that's 30 cents or what that is. On your Inspire, if you hit the up arrow and hit enter, it'll show you what that number is. Looks like $52,780.32. $52,780. And I forgot my number already, and 32 cents. So there's some compound interest and a little calculator work while we were at it too.